All right, or what we call in a fancier term, the rate of our reaction. Okay, so what we're going to do is we're going to look at a very simple chemical equation here, simple in that it doesn't involve very many compounds. All right, we're going to take nitrogen dioxide gas. This will actually react with itself to form dinitrogen tetraoxide gas. All right, so this is our chemical reaction that we're going to be studying here. And what we're going to do to study the kinetics of this reaction is we're going to take this nitrogen dioxide, we're going to measure the concentration that we have, and then we're going to start the clock. We're going to kick this reaction off, and we're going to see how that concentration changes over time. All right? So what I'm going to do is I'm going to keep track of our nitrogen dioxide here in red and my product here in green. And we're going to build this graph where on the one hand we have concentration on our y-axis and we have time on our x-axis. All right, and again, I'm going to start this reaction here with only, whoops, this is going to be a common problem with this here, with only our reactant in this flask. So at t equals 0, all the way over here on our x-axis, t equals 0, we only have that red in our flask, our reactant, and we have none of our product in there yet. Okay? So now we're going to start the clock. We're going to kick this reaction off here. What's going to happen to the concentration of that reactant over time? Is it going to increase or decrease? It's going to decrease because our reactant is getting converted into product as this reaction occurs. And what's going to happen to our green line? Is it going to increase or decrease? It's going to increase because that is our product, right? So at the end of the day, we're going to get a curve that looks something like this. The exact shape of the curve is unique to each experiment, but this is typically something that you would see for these types of reactions here, for this type of experiment. Okay. Again, we can tell that the red represents our reactant because reactants get consumed in our reaction. They decrease in concentration. I will kill you. This was the backup to the backup to the backup. Okay. Woo. All right. Anyways, reactants, we can tell that the red curve is our reactants because it's decreasing in value, and we can tell that the green curve is our products because it's increasing in value. Okay? The other thing that we want to note about this curve here is we actually see this stoichiometric ratio in this curve as well. Notice that my red curve starts out at a value of 2. And when my green curve starts to form, it levels out at this value of 1. So at the end of the day, when all of my reactant is consumed, I only have half as much product. Voice crack, all right? That's because we start out with that stoichiometric ratio, that 2 to 1. Oh my God. Okay, that 2 to 1 ratio. Let's see here. It's actually this thing. Okay, anyways. Cool, so this is going to be a fun lecture. All right, so yes, anyways, we see that stoichiometric ratio come into play as well, right? So you want to convince yourself that our red curve starts out at twice the value of what that green curve levels out at. And that's because we need to consume 2 molecules of that nitrogen dioxide for every 1 molecule of product that's formed. Cool, so we said we're going to be concerned with the rate of our reactions here. So our rate would be the change in concentration over the change in time. Okay, you would have encountered rates in a physics class as well, right? You would have talked about, oh, sorry, this is going to happen a whole bunch, my bad. Just let me know if it's not on the screen. You would have talked about rates in your physics class as well, right? You would have learned about distance, and then the rate of change of distance is known as velocity. All right? If we're taking our concentration, what's on our y-axis here? Right? Change in concentration on the y-axis divided by change in time on the x-axis. What does that correspond to on this graph here? Change in y over change in x. It's the slope, absolutely. Rise over run, right? So absolutely. This is the curve that we can get. We can get curves like this fairly easily in chemistry. Measuring concentration is something that we have like 100 different tricks to do in chemistry. It's something that's very important. So being able to measure how concentration over time changes, that's very doable. When we're talking about kinetics, what we're interested in is the slope of these diagrams here, the slope of these graphs. So absolutely, our rate here, this is going to be the slope of that concentration versus time graph. All right, so we got a few different rates that we're going to be concerned with. All right, we did our reactants in red, so I'm going to keep that color scheme going here. For our reactants, if we want to know how that concentration changes over time, this is what we call the rate of consumption. Because our reactants are consumed. Okay, that would be equal to the rate is equal to the change in the concentration of your reactant divided by the change in time. All right, so we call it the rate of consumption when it's our reactant because reactants are being consumed. All right, now if we look at this graph here, let's see if we can sort of figure out a little bit about our rate of consumption here. Again, looking at this red curve. If I just pick 2 points here, we'll pick these very 2 first points. I'm going to draw this line to approximate my slope here. What would we expect about the value of that slope? Would it be positive or negative? Negative, right? Because our reactants, again, they're being consumed. So your rate of consumption is going to be a negative value. All right, we were keeping track of our products in green. Okay, for products, if you think we would call it the rate of production, that'd be a pretty good guess, but instead we call it the rate of formation. Okay, and so the rate of formation is equal to the change in concentration of those products over the change in time. All right, so again, let's go back to this graph here and see if we can't qualitatively understand something about our rate of production here. Again, I'm going to take those first 2 time points. I'm going to draw this line here. All right, what will we think about the value of that rate of production? The sign of our slope here for the rate of production should be what? Positive. And again, that's because we're producing this product. So this should give us a positive value. All right, cool. So let's take a look at the data that actually made up this graph. We're going to do a little math, see if this checks out. All right, so here's our same graph. We now have the table, our value for time, our value for the concentration of our reactant, the nitrogen dioxide, and the value for the concentration of our product. All right, so I'm going to pick these first two time points here. And let's go ahead and calculate that rate of consumption. We said that that was the delta concentration of reactant over delta T. All right, so what does that mean? That means I'm going to take the concentration of one of those time points. We're going to pick the larger of the two. All right, so time point, or rather data point 2 minus data point 1, concentration, divided by the time of data point 2 minus data point 1. All right, I'm going to put in my actual reactant identity here, that NO2. Okay. One thing I want to be just kind of super duper clear on here that I keep on using over and over and over again because we need to be familiar with it is this sort of bracket notation here. What do I mean by these brackets? Concentration, right? So concentration of whatever's in the brackets. That's what that notation means. Cool, so I'm going to pick these specific time points here. My 1.213 minus 2.000 divided by 0.50 minus just straight up 0. Okay, punch that into my calculator. I get a negative, which is good because we're talking about a rate of consumption here. Negative 1.574. If we're being good with our sig figs, we should have 2. So I'm just going to kind of mark that with a bar. All right, and now let's think about the units for this rate here. Okay, I was kind of sloppy when I put in these numbers. I didn't use units. What are the units of that numerator? Molarity. And what are the units of the denominator? Seconds. And nothing cancels out there, right? I don't have any sort of units that are canceling out. And so our rates are going to be in these mixed units of molar per second. Okay? And that is typical for our rates of consumption, formation, reaction, whatever it is. We're talking about the change in concentration over time. That, you may see instances where it's concentration over minutes or something like that. We are going to default to that IUPAC standard, the seconds. But yes, concentration over time is our rate units. Okay, great. So now y'all are going to take a second and tell me for that same time point, calculate that rate of formation of our product. Okay, and so typically when I have you guys do this work on your own, what I'll do is I'll give you a little bit of head start, and then I'll kind of quietly start filling in so you can look up if you're a little stuck, and then we'll go through it together. All right, so I take that second data point's concentration, subtract that first data point, divide it by that change in time, and I get 0.76. Again, our units are in molar per second. If I'm being good, we're going to mark those two sig figs. Okay? So first of all, we proved what we had said about the slope, right? I think we could tell that just by looking at the graph, which is great, right? The sign of that rate of consumption is negative. The sign of that rate of formation is positive. But let's take these and stack them next to each other real quick. All right, is the rate of consumption equal to the rate of formation? No, they're not the exact same value. But can anybody see how they're related here? That's stoichiometric ratio. Absolutely. This value is exactly twice that of the rate of formation. We can be even fancier here. We can say this rate of consumption times 2 equals, I guess times negative 2 if we're being good, equals that rate of formation, right? So again, we see that stoichiometric ratio that comes into play. We can't have them both being consumed at the same rate because in our stoichiometric ratio, we're going to have twice as much NO2 being consumed as products being formed.
Isn't the 2 on the other?
Oh yeah, you're right, my bad. Doop. Making sure we're paying attention. Yeah. Cool. All right, the other thing that we want to note just from this graph, again, we're kind of putting into practice here our calculus skills of looking at curves, okay? Let's look specifically just at this red curve here. And let's note the slope at the very beginning is rather steep, right? Does this slope remain constant throughout this reaction? No. As we move along in time here, this line's getting shallower and shallower and shallower, right? Until it'll eventually flatten out completely. And this is very typical. Typically speaking, for a reaction, the rate of that reaction will decrease as that reaction is occurring because you're using up that reactant, right? Reactant molecules are being decreased in concentration as this reaction is occurring. There's just fewer of them there to react with one another. Cool. All right, so we got these rate of consumption, rate of formation. There is another very important one, the one that we're actually going to focus on kind of the most here, and that is the rate of the reaction. All right, for each reaction that we study, we want to just give it a value that corresponds to how fast or slow that reaction is going. So this is going to be closely related to those two rates that we talked about before, consumption and formation. All right, with kind of two important caveats here. When we're talking about the rate of a reaction, we always report those rates as positive values. Okay? The other thing that's going to be really important about this rate of reaction here is we want this rate, this value that we get, to be the same regardless of what we measure. Meaning it shouldn't matter whether I was measuring the concentration change of my reactant or the concentration change of my product. I better get the same value for my reaction rate regardless. Okay? In our graph here, we had both plotted, right? We had both the increase in our product concentration and the decrease in our reactant concentration. Sometimes it's way easier to just measure one of the components of a reaction. And we want to make sure that whatever component we measure, we always get that same value for our rate of our reaction. Okay? So, taking our little simple example here. Okay, again, this is our 2NO2 going to N2O4. Okay, if we want our reaction rate, all right, we want to be able to find that using that rate of consumption or that rate of formation. Right? Regardless of which one of these we measure, we should be able to get the same reaction rate here. All right, but we got a bit of a problem here. Currently, these two are not equal to one another, right? We just established that by doing that math here. So first of all, I got to square away the signs. And again, we said that that reaction rate is always going to be positive. So what am I going to do to my reactant side concentration here? It's already negative, so then I'm going to make it positive. How do we do that? Multiply by -1, right? So we're going to stick a negative sign out here in front of this one, and only in front of this one. And we're going to note that's because it's one of our reactants. All right, but even if we square away the sign, as we showed when we did our math here, the value still is not going to be equal to one another because of that stoichiometric coefficient. So we're also going to factor in that stoichiometric coefficient to our expression. What we're going to do is divide by that stoichiometric coefficient. Okay, and where does that 2 come from? We're going to say because of our stoichiometric coefficient. All right, so the rate of our reaction, if we measured the rate of consumption, we'd have to flip the sign and divide that value by 2. It's actually just equal to the rate of formation of our product in this example here, but this is how we can get our rate of our reaction. Okay, so I'm going to put up a new balanced chemical equation, and you're going to give me these equations that we need here. All right, so let's take a look at another one. We're going to take fluorine, combine it with nitrogen. This will make nitrogen trifluoride. And I want you to give me that expression for the rate of our reaction. First, based on that rate of consumption of fluorine, but that should be also equal to if instead we measured the rate of formation of that nitrogen trifluoride. What's up?
How come we're only using one of the reactants?
We could have done the other one just for the sake of time. I'm just doing it. And again, it should be equal no matter what you measure, right? But yes, you could do the nitrogen as well, just for fun. All right, now I'm being a little tricky here. What is the first step you're going to have to do here? Balance that chemical equation, absolutely.
Has a coefficient too, or should all the coefficients be with the reactants?
It may, you may have a coefficient on your product as well. Yep. All right, so if I'm going to monitor the rate of consumption of that fluorine, in order to get my reaction rate, I'm going to have to flip the sign and divide it by that stoichiometric coefficient of 3. Right, so to be clear, where did that 3 come from? Just came from that stoichiometric coefficient. All right, what about if I measure the rate of formation of that product? What should the sign be? It's cool, I'm good there, right? Don't have to add anything. I do still have to divide by that stoichiometric coefficient of 2. Again, where did that 2 come from? Just from my balanced chemical equation. All right, cool. So let's use these formulas real quick. Let's say if the rate of consumption of that F2 is negative 0.115 molar per second. Let's figure out what our reaction rate is. We can also ask, what is the rate of formation of that product? All right, so everybody take a second. See if you can't tell me what the rate of this reaction would be, as well as what the rate of formation of our product would be. right, so if we look at our equation here, we're going to take a portion of that. Rate of the reaction equals to negative 1/3 delta F delta T. All right, to be clear, the rate of the consumption of fluorine is this term right here, right? So all I'm going to do is I'm going to substitute in my negative 1/3 times that value that's given to me for that rate of consumption. I'm going to be good and put my units in here. And I get negative 0.038, a bunch of threes repeating. What is the unit on that rate of our reaction? Molarity per second, right? Nothing canceled out math-wise here. Okay. What about if I'm being good with sig figs? Our rate of rate of consumption that's given to me has 3 in this problem. What about that 1/3? Doesn't have a decimal, but where do we get it from? We got it from this stoichiometric ratio. What do we know about those stoichiometric ratios? They are exact. So that 1/3 is never going to limit our sig figs. So we just need to report as many as we had in our initial rate here, or that negative 0.0383 molar per second. We'll put a box around a final answer.
So there's 2 negative signs. Wouldn't they cancel out?
They do. Positive and a good because it's a reaction rate. My bad. All right, cool. So now what about the rate of formation of our product? Okay, let's take a look at our expression here. Again, we said in red, this was the rate of our consumption of that fluorine. The rate of formation of our product is just going to be this term here. All right, so in order to solve for that green term there, in order to solve for our rate of formation, I'm going to multiply both sides by 2, or take negative 2/3 times that rate of consumption. Okay, we get 0.7666 repeated. Again, our units are in molar per second. And how many sig figs should we report to?
3.
That same 3. So final value here, 0.0767 molar per second. What's up?
So are they not supposed to be equal yet?
Say it again.
Are they not supposed to be equal yet?
So if I calculated the rate of my reaction, regardless of what I measured, I'd have to get the same value. But my rate of production does not have to equal my rate of my reaction. And that's what we solved for the second time. Okay, so we're being a little lazy by calling this the rate of our reaction. We're going to learn some vocab here. All right, what we really should have been calling it based on how it was calculated was our average rate of our reaction. Oh, sorry. Okay, this is the rate that we calculate over a given time interval. Okay, so what do I mean by that? Remember how we calculated that rate of reaction using that data before? Right, we had to take these two time points here and take the difference between them. So what we sort of did visually, let me grab a better looking graph here. What we sort of did visually is we approximated the slope of this graph by drawing this little linear segment here. All right, we made this little line, we calculated the slope of that line, and we called that the rate for that interval. And then we could do the same thing over here. And we could do the same thing over here, right? These would be the average rate of our reaction. And we can see it doesn't do a terrible job of approximating the shape here, but really this thing is a curve. Right? So if we were being really good, we would instead have treated this thing as a curve and have calculated instead what we call the instantaneous rate of our reaction. Okay? Where we take each time point and we draw our tangent line and calculate the slope of that tangent line. And this is something that is way more difficult to do. All right, but now that we got these fancy computer programs, we can do it fairly easily. Or, the big brains in the science department can. All right, so we have our average rate of reaction. This is calculated over a time interval, or we have that instantaneous rate of our reaction. This is when we calculate the rate from the slope of the tangent to each data point. Now, in fancy calculus speak, what would this instantaneous rate of our reaction correspond to of this curve? If we wanted to know the slope at every single point along this curve here, what do we call that in calculus? The derivative, absolutely. So don't worry, I'm not trying to scare you. We don't do any calculus in this class here. But important to note here, the instantaneous rate of our reaction, that is the same thing as the derivative of that concentration versus time curve. Okay, and the last sort of important vocab word we're going to learn here is the initial rate of our reaction. All right, this is that instantaneous rate but specifically at that very earliest time point on our graph at t equals 0. Okay, so again, just kind of going back here visually, what would our instantaneous rate here, what would our initial rate be? If I took that very first time point and I drew my tangent line to this curve, that would be the instantaneous rate of our reaction. When the reaction is going its absolute fastest here, right at the beginning, right? That's the that's the initial rate of the reaction. Okay, cool. This initial rate business, we're going to talk about this term here again in a second, but we got to jump on. So now we're going to talk about what we call the rate law. Okay, so step one when we're doing a kinetics experiment is to get that concentration versus time information, all right? Now we're going to move on. Now we're talking about rate law. This is a different concept here. This tells us how the rate of the reaction changes as a function of reactant concentration. Right, so we talked about how that concentration changes over time. That's the rate. Now we're going to look at how the rate of the reaction changes if we add more stuff to it. All right, so we're going to start by taking a look at just a very simple example of a chemical reaction. We're going to say some reactant A being converted to product. Just a one reactant reaction here. All right, we can give it a stoichiometric coefficient of little a. All right, my rate law is going to be this function that relates the rate of this reaction to the concentration of that reactant. All right, and it turns out that our rate laws, you study a whole bunch of different reactions and they all fall into this same sort of pattern of what the rate law looks like. The rate is equal to some constant K times that concentration of A raised to some power. All right, so this is our rate law here. Again, it relates, like we said, the rate of our reaction as a function of reactant concentration. And now we got these two unknowns here, what we call our rate constant K. All right, so let's label these. So we call a rate constant. All right, and that concentration is raised to some power, this m here, what we call the order of our reaction. Okay? Cool, so it turns out that they study, all the big brain chemists go out there, they study a whole bunch of different reactions, and it turns out that 90% of them fall into one of three buckets with regard to the order of our reaction. All right, so let's talk about reaction order here. All right, either M is equal to 0, what they call a zeroth order reaction. Oh, whoa. Okay, so let's take this rate law and plug in that value for M. We're going to have our rate is equal to some constant K times the concentration of A. And now we get to plug in our order, our value here of 0. Okay? How can we simplify this expression here? What's that concentration of A to the power of 0? What's anything raised to the power of 0? 1. So that means that this just becomes K times 1, or just K. So for a zeroth order reaction, what's going to happen if I change the concentration of A? Is that going to have any effect on my reaction rate? No, that term doesn't appear anywhere in this equation at all. So for zeroth order reaction, we're going to note the rate is independent of that concentration of A. Okay? So m equals 0, that's one bucket here. The other one is when m takes on a value of 1, what we call a first order reaction. All right, again, we're going to take that rate law. We're going to plug in that value of 1 for m. We get our rate is equal to k times a to the power of 1, which is just the same thing as saying there's no exponent there at all. Okay? Cool. So if for a first order reaction, does the rate depend on the value of our reactant concentration? Yeah, now that does appear in that term there. Okay? So let's sort of think a little bit more about exactly how it's going to depend on that. All right? What happens if we double the concentration of A? What effect is that going to have on our rate? Okay, so we got some prediction here that it's going to double the rate of that reaction. Let's plug in some numbers and see if that actually checks out. Okay, let's do a calculation here where we're going to say, all right, A is equal to, and this is the best way to do plugging in numbers, is to pick very simple numbers. The best one to pick is 1. All right, so we're going to do one calculation where we say that A is equal to 1 molar. And then we're going to do another calculation where we say that A is double that value or equal to 2 molar. Okay? We're just going to plug these into our rate expression here. So we have rate equals K now times that 1 molar. All right? And we have rate is equal to K times that 2 molar. All right, so in this first one, we get rate. We're going to ignore units for right now, is equal to K. And in the other example, rate is equal to 2K. Did we double our reaction rate? Cool, wonderful. All right, so for this first order reaction, this is what we would call directly proportional. If you double your reactant concentration, you're going to double your rate. What if I triple my reactant concentration? It's going to triple my rate, right? If I cut my reactant concentration in half, what's going to happen to my rate? It's going to cut in half, right? So these are what we mean by directly proportional. Okay. If we double the concentration of A, we double our reaction rate. All right, and then the third bucket is when that value of m is equal to 2, or you guessed it, what we call a second order reaction. All right, so if we go and plug this into our rate law here, we get that the rate is equal to some constant K times the concentration of A, but now raised to that power of 2. Is the rate going to depend on the concentration of A for a second order reaction? Yes. Okay, so again, that concentration appears in that term here. And let's ask ourselves the same question here. I want you all to take a stab at this here. If we double that concentration of A, I want you to tell me what's going to happen to the rate of this reaction. Okay, everybody take a second. See if you can apply that same logic we did before. Tell me what's going to happen to the rate of our reaction. All right, so again, I'm going to take, say, in one instance, we're going to take our concentration of A to just be 1 molar. We're going to do another experiment where we double that concentration to 2 molar. We're going to plug this into our reaction, our rate law here, and we get rate equals K times 1 squared. What's 1 squared? Just 1. So this is rate equals K. But over here, I have rate equals K times 2 squared, 4. All right, so if we double our concentration of A, now we quadruple the rate of that reaction. All right, so for second order reaction, we double A. I'm going to say 2 to the 2, right, because it's really our exponent here, our rate. So importantly, what if we tripled the rate of our reaction? I'm sorry, what if we tripled our concentration of A? What effect would that have on the rate of our reaction? By 9, right? 3 squared. Your factor to the power of 2 is going to be the difference here. Okay, cool. So again, where did we kind of got walking down this sort of order rabbit hole here? What the heck did that mean? We said that when we study a reaction, we can build this rate law here, right? It relates our rate of our reaction to the concentration of A. And we got these two terms, our rate constant K and the order of our reaction. It turns out that if you go out there into the wild and you study all the chemical reactions, 90% of them will fall into these 3 buckets. They'll either be a 0th order reaction, a 1st order reaction, or a 2nd order reaction, okay? And these ones are particularly easy to spot based on what we just discussed. So what do I mean by that? I'm going to put up some data here, okay? We're going to look at the concentration of reactant. We're going to do a whole bunch of experiments where we measure that initial rate of our reaction. All right, and you're going to look at this data here and tell me what the order of this reaction is. Oh, my bad. All right, so we did a whole bunch of kinetics experiments. We gathered some data about how this rate changes as a function of concentration, and we're going to analyze this data to figure out what the order of this reaction is.
That subscript 0 on the concentration of A, what does that mean?
It means it's the because the A gets consumed
yeah.
over, so it's how much you put in initially.
Okay.
Yeah, that's a good point. We'll make a note of that.
What they call it, like A naught or something?
Yeah, A naught.
Yeah.
All right, so let's see. Let's take a poll here. Who thinks that this would be a 0th order reaction? What about a 1st order reaction? All right, what about a 2nd order reaction? Cool. So this is indeed a 1st order reaction. So how can I tell that by looking at this data here? All right. Well, what I want to notice is that between this 1st and 2nd trial, what happened to my concentration? I doubled it. And then if I look at my rates, what happened to the rate of this reaction? It was also doubled. Right? Likewise, I can pull in that 3rd data point. I took that first one, multiplied it by 3. And what happened to the rate of that reaction? It was also tripled, right? So this is this 1st order reaction here, this direct relationship between the concentration of A and that rate of that reaction. Cool. So that's all well and good when we have a data set that has relatively easy to look at numbers. But what do we do when we get a big, ugly data set? All right, so let's look at another one here. We're going to do the same thing, the concentration of A initially. Versus that initial rate. All right, now, unless you got some like Goodwill Hunting calculator brain going on here, it is very difficult to see the pattern that you would have to apply for a 1st, 2nd, 3rd order reaction here. All right, so we're going to call this section here how we calculate our rate law. Okay, and this particular lecture, this portion of this lecture will give you a little bit of an insight into how the math in Chem 1B is a little bit different than the math in Chem 1A. We're going to have to use a little bit more intense algebra here. Okay, again, let's just remind ourselves of what we mean by our rate law. That's that expression that tells us that our rate is equal to some constant K times the concentration of A raised to some power. All right, so to be clear, I have 4 terms in this expression here. Which 2 are in my table? Concentration, right? So this would be one of these terms in my rate law. And what's the other one? My actual rate. Okay? Cool, but herein lies kind of the problem and why we're going to need to use some fancy algebra, is we have these 2 unknown values, okay? So let's just be very clear. We do not know what this rate constant K is, nor do we know what the order of this reaction here. This is what we're trying to find. And since we've got these 2 missing variables, we can't just plug in numbers and solve, right? We can't solve for 2 missing variables. So we're going to have to do something of a little bit of an algebraic trick here, all right? Step 1, we got to find what that order is. So out of these 2 missing variables, we're going to prioritize that value of M, the order of this reaction. That's always going to be step 1 here. Okay? But again, I have too many missing variables, so how am I supposed to find the order of this reaction? We're going to do this trick. We're going to take the ratio of two data points. All right, so what the heck do I mean by that? All right, we're going to grab two data points, not one, because that won't get us anywhere. We got too many missing variables. We're going to have to grab two data points from this table up here. So I'm going to label these. This first one's going to be data point 1. This second one's going to be data point 2. All right, I know for that first data point, my rate law, that the rate at data point 1 is equal to that constant K times the concentration of A at data point 1 raised to that power of M. So far, so good? All right, but again, we can't get away with just one. So what we're going to do is take the ratio of two data points. I'm going to divide by my second data point, the rate at data point 2. And divide the other side as well. K times the concentration of A at data point 2. Raised to the power of M. Whoops. So step 1 here, I took the ratio of these two data points. All right, why did I do that? Anybody see how we can simplify this now? What can we do? We can get rid of K. I don't know what K is. Could be 5, could be 5 million, could be 0.5, but it's some constant value. And any constant divided by itself is just 1. Okay, so we use this little trick where we took the ratio of those two data points. All right, Y, in order to cancel out one of those unknowns that we don't know, that value of K. Now I'm down to just one variable. So now I can actually use this here and solve for that missing variable. Okay, but we're going to need to do some tricky algebra to do it here. So we're going to need to use two important algebraic expressions. The first one is that any number raised to some power divided by another number raised to that same power is just equal to A divided by B all raised to that exponent. All right, so we can gather those m's up into just one place here using this expression. So I got rid of my k's. Need this. All right, so I got rid of my k's. Now I can simplify this. This is the same thing over here as the concentration of A at that first data point divided by the concentration of A at that second data point, all raised to that same power of M. Okay? Cool, so at least now M's not all over the place. We got it in just one place here. All right, we got another problem on our hands though, which is that it's stuck up in that exponent. So how are we going to get it down? Yes, we get to use everybody's favorite algebraic operation, the log. All right, you can use either log or natural log. We're going to be fancy and use natural log here, but the bottom line is the natural log of any number raised to some power is equal to that exponent times that log. All right, so this is going to be our way to bring down that exponent. So these are these two kind of fancy algebraic rearrangements that we need here. okay? Now, I'm trying to bring down this value of m over here on the right-hand side. So again, we're going to take the natural log, but I can't just take the natural log of one side, right? Remember, rules of algebra, you can do anything you want to this equation as long as you do it to both sides of this equation. So in order to use that natural log here, I'm going to have to take the natural log of both sides. All right, so this is going to simplify to the natural log of that rate ratio. Let me just move this up here. Is equal to, we got our exponent m down, the natural log of that concentration ratio. Okay? Cool. So this might look big, ugly, and scary, but let's just take a look at where we started here. I'm going to recopy this table down here. In my expression here, do I know what rate 1 is? Yeah, that's just the rate of that first data point. So I'm going to plug that in there. I know what rate 2 is. That's just the rate of that second data point. I also know what my concentration is of that first data point and my concentration of my second data point, right? And I don't know what, bottom line is the natural log of that ratio. It's just going to be some number. So now we can just plug in and solve. All we have to do is rearrange this equation here and solve for that one variable that we don't know that value of m. All right, so everybody take a second. See if you can't tell me the order of our reaction here, given our data analysis. All right, and after all that hard work, what do we get for the order of our reaction here? 2. So this, buried in this big ugly data set here, is just a second order reaction. So now what we would do is we're going to go back up to our rate law, right? We said we were trying to find these two values here, our rate constant K and our order. Well, now we've done one of them. Whoops. We're going to substitute in for that order a 2. All right, and now we got one more missing variable, our K, our rate constant. You may see how we're going to do that. We're going to leave that here for today, and we will pick up with rate loss stuff next class period. Okay? Any questions on this before we wrap it up? Cool. All right, so we're going to take our break. We'll meet back here in 15 minutes. We got a lab activity to do.